Welcome to G Fun Facts Online. Today we are going to dismantle a 50-year-old myth about our neighbor, the Red Planet. For decades, the prevailing narrative of Mars was one of a geologically dead, frozen wasteland. It was seen as a fossil of a planet, a place where history stopped billions of years ago. When we looked for life or organic chemistry, we looked with a binary mindset. We thought either we would find the remnants of ancient microbes, or we would find a sterile pile of rocks. But as of early 2026, that binary view has been completely shattered. Discoveries from the Curiosity and Perseverance rovers, alongside advanced analysis of Martian meteorites, have revealed that Mars is a chemically active world. It possesses what scientists are calling an endogenous organic engine. This is a suite of geologic and electrochemical processes that generate complex organic matter without the need for biology. From the mudstones of Gale Crater to the fractures of Nili Fosse, Mars is synthesizing the building blocks of life on a massive scale. In this episode, based on the article Endogenous Organic Synthesis on Mars by AI Automation Workflow, we are going to descend into the molecular machinery of the Martian crust, explore the battery hypothesis that turns rocks into fuel cells, and discuss what this means for the search for life. To truly understand the magnitude of what is happening now, we have to go back to 1976. This was the year of the Viking landers, NASA's first dedicated biological explorers. They scooped up Martian soil and ran it through a gas chromatograph mass spectrometer. They heated the soil, looking for the vapor signatures of organic compounds. The result was a shock to the system. Aside from a few cleaning solvents brought from Earth, the result was negative. Viking found nothing. For 40 years, this result cast a long shadow over planetary science. It suggested Mars was not just dead, but chemically hostile, perhaps sterilized by a superoxidizing surface. But we now know that Viking did not find a lack of organics. It accidentally destroyed them. It wasn't until the Phoenix lander in 2008 discovered perchlorates in the soil that the puzzle pieces fit together. Perchlorates are highly reactive salts. When the Viking landers heated the soil samples to look for organics, those perchlorates became aggressive oxidizers. They effectively incinerated any organic matter present, turning it into carbon dioxide and chlorobenzene before the instruments could even detect it. The organics were there. We just burned them before we could see them. The redemption of Martian chemistry began with the Curiosity rover in Gale Crater. Curiosity was equipped with the SAM suite, designed specifically to sniff out what Viking missed. By 2018, the team had announced the discovery of thiophenes, which are sulfur-bearing organic rings, found in 3.5-billion-year-old mudstone. But the real breakthrough has happened in the last few years, leading up to early 2026. By using wet chemistry techniques that protect organics from those destructive perchlorates, scientists have unveiled a treasure trove. In early 2025, they confirmed the presence of long-chain alkanes, specifically decane, undecane, and dodecane. These aren't just simple puffs of methane. These are complex chemically stable hydrocarbons. Chemically, they look suspiciously like the fragments of fatty acids, which are the structural components of cell membranes. At the same time, the Perseverance rover in Jezero Crater has been using its SHERLOC instrument to map organic fluorescence directly on rock faces. Unlike Curiosity, which has to grind rock to powder, Perseverance sees the context. It found organics sandwiched between sulfate minerals, effectively canned and preserved for billions of years. The detection of aromatic rings in the formations at Jezero proves that organic synthesis was not a fluke event, but a widespread planetary phenomenon. So if these molecules aren't coming from biology, where are they coming from? This brings us to the most fascinating part of the new research, the engine room of abiotic synthesis. Mars is effectively a giant chemical factory, driven by heat, water, and the inherent energy of its minerals. There are three main mechanisms you need to understand. The first is the concept of the Martian Battery. This hypothesis, solidified by research in late 2024, proposes that the interface between igneous rocks and salty brines creates natural electrochemical cells. Mars is rich in conductive minerals like magnetite and sulfides like pyrite. When these minerals touch a saline electrolyte, which is just salty water, they create a galvanic potential. It is literally a battery. This natural voltage is sufficient to drive the electrochemical reduction of dissolved carbon dioxide. The CO2 is stripped of its oxygen and bonded with hydrogen protons from the water. The output is a suite of organic molecules, ranging from simple formate to complex hydrocarbons. This is revolutionary because it doesn't require volcanoes or extreme heat. It can happen in cold, dark subsurface aquifers. The battery is always running, slowly trickle-charging the Martian crust with organic carbon. The second mechanism is serpentinization. This is the classic engine of abiotic chemistry, which we also see in Earth's hydrothermal vents. It happens when water interacts with ultramafic rocks rich in olivine. The reaction releases heat and produces massive amounts of hydrogen gas. In the presence of iron catalysts, this hydrogen reacts with carbon dioxide to form methane and longer hydrocarbon chains, a process known as Fischer-Tropsch type synthesis. Large regions of Mars, like Nili foci, are massive exposures of olivine. We now believe these regions were once giant reactors, pumping out hydrocarbons during the Noachian period, when liquid water was abundant. The third piece of the puzzle is nitrogen. Life needs nitrogen, but atmospheric nitrogen is inert and hard to break apart. However, recent analysis of the ALH 84001 meteorite and data from Curiosity has found nitrogen-bearing organics like nitriles and nitrates. New models suggest that the same iron-rich catalysts driving the hydrocarbon synthesis can also drive a natural Haber-Bosch process. Under the right conditions, nitrogen and hydrogen are catalyzed into ammonia, which then reacts with organics to form amino acid precursors. This proves Mars wasn't just making oil, it was making the specific scaffolding required for prebiotic chemistry. Let's talk about the specific molecules that have been found, because the inventory is more diverse than we dared to imagine. As mentioned, the 2025 confirmation of decane, undecane, and dodecane is tantalizing. On Earth, these chain lengths are often associated with the breakdown of biological fats. Finding them on Mars forces us to ask if they are geolipids, which are abiotic mimics, or fossilized remains of ancient cellular membranes. The current consensus leans toward geolipids, formed by surface-mediated polymerization, where mineral grains act as templates to line up carbon atoms. Then there are the thiophenes. These are ring-shaped molecules containing sulfur. Sulfur is a cross-linking agent, similar to how it works in vulcanized rubber. On Mars, sulfurization likely preserved organic matter, locking it into large, tough macromolecules called kerogen that could survive billions of years of cosmic ray bombardment. This macromolecular carbon is the dark matter of Martian chemistry. It is a disordered mesh resembling terrestrial coal. Geography matters here. Mars is not uniform, and specific environments acted as kitchens for this chemistry. Gale Crater was once a long-lived lake. The discovery of siderite, or iron carbonate, there is crucial because it forms only in high CO2, low oxygen environments. It confirms early Mars had an active carbon cycle. Then there are Jezero Crater, where Perseverance is exploring a delta. The margin unit there is rich in carbonates and silica, which is excellent at preserving organics. The finding of diverse organic signals in the igneous rocks of the Sciata Formation represents a magmatic source of organics, meaning they were formed from cooling magma in the high-temperature depths. And finally, Nili foci remains the holy grail for abiotic synthesis due to its massive olivine exposure. If there is a place on Mars where the soup of life was cooked, it is likely there. When we look at Mars in context with the rest of the solar system, the picture gets even bigger. On Earth, plate tectonics and voracious biology recycle carbon rapidly. We have very little record of abiotic synthesis because life eats it. Mars, lacking tectonics and macroscopic biology, is a museum. It preserves the prebiotic chemistry that Earth has long since erased. Studying Mars is studying the prologue to life on Earth. It is also comparable to the icy moons of Jupiter and Saturn. Enceladus has subsurface oceans with hydrothermal vents that are chemically identical to the serpentinization proposed for the Martian subsurface. Mars is essentially a fossilized Enceladus, a place where the ocean dried up and left the vents exposed for us to study without drilling through 20 kilometers of ice. While Titan has atmospheric chemistry driven by sunlight, Mars is a rock chemistry world, driven by the subsurface. So where do we go from here? The future lies in decoding the message these molecules are holding. The European Space Agency's Rosalind Franklin rover, scheduled for launch around 2028, will do what Curiosity and Perseverance cannot. It will drill deep. Its 2-meter drill will retrieve samples from below the radiation zone. The surface of Mars is bathed in ionizing radiation that chops up long organic chains. By going deep, we hope to find pristine, unaltered molecules, perhaps even fragile biomarkers like amino acids. Beyond that, the Mars Sample Return Campaign aims to bring the cores collected by Perseverance back to Earth. In our labs, we can measure isotopic ratios to look for the specific clumping of isotopes that biology produces. We can sequence the carbon chains to see if they follow the rule of 2, as biology prefers even-numbered carbon chains, or if they show the random distribution of abiotic chemistry. This research into endogenous organic synthesis forces us to rethink the definition of a living planet. Mars may not have biological life that we know of yet, but it has a metabolism. It breathes carbon dioxide, drinks water, and uses the energy of its rocks to build complex structures. This geochemical life is likely the default state of rocky planets in the habitable zone. Before DNA, before cells, there was the battery of the rock. Mars offers us a frozen snapshot of that pivotal moment in cosmic history. The moment when a planet starts to wake up and build the ladder toward life. Whether that ladder was ever climbed remains the ultimate question, but we now know that the rungs are there, built by the planet itself, waiting in the red dust. Thanks for listening to Fun Facts Online.